Let's just look at a couple more aspects of the ubiquity of Fourier ideas in modern life and modern science and technology. I In the digital realm, I talked about the fast Fourier transform at the end of the last video, just very briefly, emphasizing that this is still some recent innovations. Back in the '60s, even more recent. Still something going on today is a kind of a significant revolution in Fourier-like ideas, and that's the subject of wavelets. It's definitely a bit different from the pure Fourier idea, but there's no way you would study this without really mastering the basics of the Fourier story. Because again, it's a way to make functions, any kind of signals or patterns or data, out of something you might not call waves exactly, because they're not beautiful sine waves. They're pictures like functions like this red function, which looks rather bizarre when you first look at it. That's a simple building block to build more complicated things with? But it turns out that you can find functions like this that look weird but have amazingly nice properties. And a couple of the applications of the idea of wavelets is the basis of cutting-edge image compression algorithms. So, for example, this sequence of 3 pictures is using JPEG 2000, which is based on wavelet ideas, which are, again, a more sophisticated idea of the JPEG ideas that use pure Fourier. And what you're seeing here is taking an image that wasn't compressed and compressing it using JPEG 2000 to quite a bit less size. I think it's going from 378 to 11.2 kilobyte, and you really can't see the difference because of this sophisticated algorithm. This wavelet in particular is due to Ingrid Dobeschies, who is one of the absolute, maybe the preeminent investigator of wavelets. And she's actually applied this to image analysis, in particular trying to figure out if you can detect forgeries by looking at an image and analyzing it using wavelets. And there's some interesting ideas there. It's not like something you can it always works, but it's a very cool application. So the basic idea that Fourier in technology and engineering, the Fourier ideas are absolutely alive and still being developed. I want to talk a tiny bit about what I would consider maybe the deepest application of Fourier ideas. In fact, if you think about quantum mechanics, our whole world is a world of waves. It's not just that you have a choice to analyze the world as a world of waves, but quantum mechanics says that everything is a wave. Even things we think of as particles, physical objects, really have a wave-like nature to it. And to really understand this in a deep way, it really does require the deep and 20th century version of Fourier, the version of the Fourier story that took 100 years to gestate and become the foundation of much of modern mathematics. So here's a picture. The hydrogen atom, depending on how its electron is energized, is how much energy it's given, you'll have these different sort of wave-like patterns of the probability of the electron being found at any particular location near the hydrogen nucleus. Let me just do 2 slides on the world's quickest treatment of a very deep topic. If you look at the pure sine wave, if you look at this kind of oscillation, and think of that as representing an electron, remember that in quantum mechanics, that all you need to know is that this represents some measurement. There's a little bit of a step that I'm glossing over here, but it's related to the probability of finding the electron at any point. And if this wave keeps on going forever, then that means that you can it's equally likely to find that electron almost anywhere. So you don't really know the position of an electron that's represented by the pure building block sine wave. But it turns out that if you go a little further in the Fourier story, it turns out that the frequency of the sine wave is exactly proportional to the momentum of the electron, essentially the velocity, how it's moving. So this actually has a very precise momentum because you're only using one particular frequency and no others to build this particular representation of an electron. So this is something with a known momentum and an unknown position. What if you wanted to create something that seems more like a particle? This is very much unlike a particle. To create a localized particle, you need to create something looking like this lower picture, Well, to create something like this, it bulges in the middle and is very small almost anywhere else. Hopefully what I've shown you already convinces you that you're going to need to have a very clever combination of a bunch of different frequencies in order to accomplish that. In particular, to get the stuff to cancel out, to get the probabilities to cancel out over here and over here, that requires the kind of very fine cancellations that we were seeing to create the square wave in the heat story, this function that was almost constant for a long period of time. So you can do that. You can create a localized particle using a superposition of waves, but I hope it's somewhat plausible that the more you want to localize it, the tighter you want this hump to be, and the more stuff you want to perfectly cancel out, it requires more and more sophisticated use of building blocks and a larger range of frequencies. And what does that mean quantum mechanically? It means a more uncertainty in the momentum of the particle. So here's a picture of something where you have no uncertainty in the momentum. It's definite, but massive uncertainty in the position. We have no idea where this localizes. Here's something where it's localized. You have a more precise idea of the position, but you had to use a lot of different momenta to create that, and so you have a much less definite idea of what the momentum is. That's the uncertainty principle. So it turns out the uncertainty principle, one of the deepest ways to understand it, is it's a fundamental statement of how Fourier synthesis works. So that's all I wanted to say about the applications. I want to go back to the mathematical story, which is really kind of why I wanted to give these lectures in the first place, because it's very cool how this one subject of Fourier analysis was a big driver, not the only driver, but a very, very big driver for 100 years of massive changes in mathematics. So why was the Fourier story so confusing? Let me talk about some fundamental issues. What is a function, really? And our notion of what a function is and what you should do with it and how you should think of it changed a couple of times in a very big way due to the Fourier, the conundrums posed by Fourier. What do infinite sums mean, and how do you deal with them carefully? I alluded already to the fact that people had been dealing with infinite sums, especially infinite sums of numbers, for quite a while, but they really didn't really understand them. When do infinite sums work or fail? And they thought they understood them to some extent, but they really didn't. And how does this all relate to the rest of calculus? So let's go through those issues in turn. First of all, what is a function? Well, to Newton or Euler or Gauss, basically 1600 to about 1820, a function was really a formula. It was an algebraic gadget. So y equals x cubed plus 2 over x, or to get a little more complicated using more complicated functions, y equals cosine of e to the x minus the natural log of x. These were functions, and this is how most high school students, for example, think of functions, although we try to tell them that functions are more interesting objects. In particular, they are rigid objects. If you have this kind of formula, that's going to create a graph, something like this. Well, this is actually a much simpler function. This is 1 over y equals 1 over x. It's going to have a rigid object that you can't just say, I'm going to take this guy and I'm going to put a little poke here, and it's going to go up and down and make a very different shape just at one point. You can't just mess with it in one point. If you're going to mess with it anywhere, it's going to mess with it everywhere. And so these are rigid objects. So here's a parabola. You could shift the parabola up. You could move it left or right. But you just couldn't put sort of an arbitrary wiggle in it and think of that as a simple change in the function. They are also well-behaved functions, except possibly at a few points. This parabola, this is the graph of something like y equals x squared, modified slightly. This is something that always goes on forever, left or right, and has nice behavior. It's nice and smooth. It doesn't have any gaps or spikes or jumps. This guy, y equals 1 over x, has one very notable spike to minus infinity and then to plus infinity. But there's only one place where that happens, and the rest of it is this very nice smooth curve. And one way to say that is it was relatively easy to draw the graph of things that these people would have considered legal functions before the Fourier story really made this a more interesting idea. So in the 19th century, very much prompted by the Fourier ideas, Cauchy, Dirichlet, Riemann, and Weierstrass, and many others, but these are probably the primary four to pick out, they redefined what a function meant in a very drastic and important way. They said a function is going to be any rule that takes a number as an input and produces a number as an output. So here's a example, one of the most famous examples of this new kind of funky function, what that definition allows you. We're going to define a function f that takes a real number and produces a real number. It's a very simple rule. F of x is going to be 0 if x is irrational, and 1 if x is a rational number. Very simple rule, but totally unlike the kinds of functions that I was talking about in graphing here. It's so weird that it's almost impossible to actually graph this function, because it's going to be 0 at root 2, for example, but then it's going to be 1 at any rational approximation of root 2, like 1.414. And no matter how close, as long as it's rational, it's going to jump to 1. This function jumps back and forth between 0 and 1 amazing, just infinitely often on any interval. It's a very weird function to try and graph. Here's one that's a little easier to graph, even though the definition is a little more complicated. So we take f, there's a new function f, we apply it to any rational number, and we put that rational number, by definition a rational number is an integer over an integer, p over q, and we put it in lowest terms. And we just take 1 over the denominator. We just basically turn the numerator into 1. And we define f of an irrational number still to be 0. So here's what that looks like on the unit interval. Here's f applied to 1/2. F of 1/2, you don't even have to change the p, it's 1/2, okay? F of 1/3 and 2/3 are both 1/3. F of 1/4 and 3/4 are both 1/4. F of 1/5, 2/5, 3/5, and 4/5 both are all a fifth, etc. Okay, and so what you see is there's a few blips that get these relatively high values, but most of the values are very small, because most rational numbers, to express your average rational number, you're going to need a very large denominator. Like if you pick an average rational number, it's probably going to be like 5,407 over 3,921 or something like that. And you're not going to be able to reduce it. And in fact, and of course, all the irrational numbers are supposed to be totally down here on the baseline. So this is a function that just keeps going blip, 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 up and down in this weird pattern. Absolutely unlike this kind of curve that's this nice continuous function where you can draw it without lifting your pen. So people like Dirichlet said, this is something we should allow as a legal function, and it's going to behave very differently from the functions that people like Euler would have wanted to create. Okay? They can be ill-behaved everywhere, not just at one point, like 1 over x was, everywhere. So this is actually still the modern technical definition in most cases of a function, any rule from inputs to outputs. It's what we try to emphasize when we teach high school students about mathematics. But there are sort of different perspectives on functions that I'm going to show you in a minute. Okay, so what does this have to do with Fourier? One of the things it has to do with Fourier is that the Fourier method, it's very easy to take sine waves and create very unpleasant looking functions. Functions that are almost as badly behaved as these guys. Not quite like this, but here's an example. Basically things where the graphs have a fractal nature. And this is not how they would have said it, of course, in the 19th century, but now we can use this kind of terminology. So here's a very famous example due to Weierstrass. It's a function where you can theoretically draw it without lifting your pen. It's called a continuous function. But at no point is it nice and smooth. It's not just that there's a lot of jaggies. The point of this is supposed to be if you zoom in on any part of this function, it will continue to be jaggy everywhere in your picture, and no matter how much you zoom in. That is very, very weird, and it really shocked people that a function could be continuous. So it's not something that jumps up and down and has lots of gaps in the graph. It's one contiguous line to graph the thing, and yet at no point, not even a single point, does it settle down and not be jaggy. If you've had any experience with fractal pictures, we're actually much more comfortable with this kind of idea now in the last 20 or 30 years, that if you zoom in on it, it's always super, super complicated. But that was a real shocker back then. And the interesting thing is not only that this function exists, it's that it's actually almost not trivial, but it's really quite easy to create this out of the right combination of sine waves. And that's exactly what Fourier says should really be legal, because from the Fourier perspective, there shouldn't be anything wrong with taking pretty much an arbitrary combination of sines. So Euler and those folks would have said, this is just not legal. This is not what I consider to be a function. But the Fourier method is saying, no, we should take this seriously. Another question is, are they useful? Okay. And then another question is, wow, how to deal with these guys? Most of the methods of calculus start to break down because they assume that at most points on the graph, you'll have things like a tangent line, a nice slope, a well-defined slope, and it will look smooth. That's not true about these guys. Okay. So what about the are they useful question? If they aren't useful, then maybe they're just a pathological example that only a very few number of mathematicians will be interested in. Well, they're actually incredibly useful. Financial modeling, for example. Here's a bunch of samples of a model of financial markets from various countries. And what you can see is that these look suspiciously like the nasty graphs I just gave you. If you look at financial graphs, they have this kind of feature that they're jagged, they go up and down, and if you magnify them, even to a pretty small scale, even to the scale of minutes nowadays, that trading is so frequent and heavy, you're going to see some oscillation, some jaggedness at almost any scale. And so the actual nicest mathematical models of many financial instruments and indices is exactly this kind of function. In physics, a very famous example, this goes back to Einstein, and a lot of people from maybe 1900 to 1930 figured out the mathematics of this. Brownian motion, if you put a little particle of something in a fluid, if it's small enough, it will be bounced continually, little bits one way and the other, by the thermal motion of the molecules in the fluid. And a very good mathematical model of that is this kind of thing that at all scales there's at least a little bit of jaggedness. Almost any random process, you won't be able to understand it. Even if it's not fundamentally jagged like this, you won't be able to get a good understanding of it unless you understand these guys, because they actually turn out to be some of the most fundamental random processes, things that are jagged at all scales. Climate modeling is a great example, where you get oscillations in temperatures maybe over the scales of millennia for ice ages, of decades for drought cycles or various variations, and certainly oscillations on the scales of years, months, weeks, days, even minutes, if, say a thunderstorm passes by. So very, very important examples of why you would want to understand these functions, things that the 18th century mathematicians would have just, they would just have said, this isn't mathematics. They would have said, we don't even want to try to analyze this, much less judge whether it's useful. Okay, so I'm going to talk in the next video. I'll talk about not necessarily strictly a new definition of function, but a new perspective on functions that actually deepens this and connects it even further to the Fourier story.